Welcome to lesson 30 already of our friendly introduction to abstract algebra. In the next few videos we are going to take an in-depth look at cyclic groups. Okay, first we lay the foundations, and basically we know already most of this stuff, so this is merely a recollection of things we have done before, spread out through the whole course. So that's why it says recall here. So as always, G is a group, and we take a subset capital X of this group, and then we ask ourselves, what is the smallest subgroup of G that contains this subset? Because the set itself, of course, need not be a group. And it is this guy here, X in these pointy brackets, called the subgroup generated by X. And here's the abstract definition. You take all the subgroups of G that contain the set X. This is what is written here. And then you take the intersection of all these subgroups satisfying this. This is not the empty intersection because, of course, G is a subgroup of itself that clearly contains X. So this might end up being all of G, but in general it will be smaller because there will be more subgroups that are smaller and containing X. And if I take the intersection of all these, I end up with a subgroup. In the very beginning of this course, we argued that the intersection of subgroups almost trivially is always a subgroup again. And clearly, because I take the intersection of all these subgroups containing X, I end up with the smallest subgroup. Okay. This, of course, is not very good to work with. If I have a large group and have to think about all the subgroups that contain this set and then take the intersection, there is a much more useful characterization of this set here. And whereas this here is a definition that is well defined, this equality has to be proved. Proved. And we did this. I think we left out some of the details because it's rather technical, but I gave you the idea in lesson, I don't know, I didn't look it up. We showed that the elements of this subgroup generated by X are of the following form. You take elements of X, of course. Then you take either the element itself, meaning this exponent here is 1, or you take its inverse, because you need, of course, all the inverses for it to be a subgroup. And then you take the product with another, or maybe the same element, it doesn't say here, of the set X, again, xi itself or its inverse, and so on. And these things here are called words in elements of capital X. If you take all these words where the exponents are either 1 or -1, you end up with a group. And this is actually the smallest subgroup containing X. And the complete proof, as I said, is a bit technical, a bit awkward, but it can be done, elementary. And we will be using this here in the special case of a singleton set. So now the only special case that is of interest for us here is when X is a set consisting of a single element. Then, by abuse of notation, we write it like that. It should always be written like that, because here in this definition, X must be a set, and small x is simply an element of G, not a set, so I should write it like that, but no one does that, so we simply write small x in these pointy brackets, which is defined to be this here, and then we use this definition. This is pretty easy here because all the xi's are one and the same element, namely x. So what does a word look like? A word looks like that. For example, like so. X to the power of 1 times x to the power of -1, so meaning x inverse, times x to the power of 1. This would be such a word for the case of n being equal to 3. Now, of course, this here cancels, and this word would end up being x itself. So nothing new. Another word could look like that. X to the 1 times x to the 1 times x to the 1. This would be the third power of x. And so on. And of course, I could have here x to the -1, x to the -1, x to the -1. which would mean x to the minus 3, which would be the same as the inverse of x to the third power. So clearly all the words end up being simply such a power, x to the m, where m can be any integer. Yeah, of course I end up with if I take this word, x inverse x, I end up with the identity, which of course must lie in this guy here if it wants to be a subgroup. And this can be defined as x to the power of 0, so that all the known potency rules, power rules hold. So the exponent can be 0, or as explained before, it can be 1, 2, 3, 4, minus 1, minus 2, minus 3, and so on. So this definition shrinks down to all these powers where m runs through all the integers, and this is the cyclic group or cyclic subgroup. If I'm in a larger group, x was supposed to be an element of a larger group generated by the single element x. All right. As I've said before, we've encountered all these concepts before, but I think it's important to collect them here on one blackboard so that you know what we're talking about. So another notion that we already know is the order of an element. The order is, of course, x is an element of the group G again. This is the smallest natural number such that x to the power of n is the identity of the group. Be aware that in my case the natural numbers do not contain 0, because otherwise it would be a senseless definition, because x to the 0, as we just had here before, would always be the identity. So this is the smallest positive integer. So the numbers 1, 2, 3 and so on, such that this holds. And this number I call O of x, the order of x. If there is such a number, of course. In finite groups, there always needs to be such a number, because otherwise I would get infinitely many different distinct powers. But in infinite groups, there need not be such a number. So if there is no such n, meaning that x to the n is never the identity, no matter what n is, what kind of natural number I plug in there, then we write that the order of x is infinity. And we say x is of infinite order. And this only can happen if the group itself is infinite. Okay, now we come to proposition 30, which contains some elementary facts that will be crucial for the rest of chapter 11, cyclic groups. So as always, let G be a group and x be an element of G, and let the order of x be a finite number n, at least for the assertions 1 to 4. This here is very, very important. And we also encountered this, I think, on some exercise sheet about the symmetric groups, I think. Whenever x to the m is the identity, of course, m is a natural number or an integer. Whenever this is satisfied, I know that n must be a divisor of m. And if and only if, so both directions. If this is satisfied, then n is a divisor of m. And although the other way around, if n divides m, then I know that x to the m must be the identity. Very, very important in a lot of steps. So next, already we also know this in concrete examples. The cyclic subgroup generated by x consists of all these powers here, from the identity, then x to the 1, x squared, and so on, up until x to the n minus 1. And this is an additional assertion. The order of this set is exactly the order of x, namely n. And you could say, well, those are n elements. Yes, but they need not be distinct. For example, x squared could be the same as x to the n minus 1. We are going to show this is not possible. These are all distinct elements, so the order of this set is exactly n, namely the order of x. This is also basic, but very important. Now for a finite group, I always have that x to the power of the order of g is the identity. This is sometimes called Fermat's little theorem. Of course, you all have heard about the big theorem that was proved by Wiles. But this, of course, is much easier to prove. And this is new. I think we haven't encountered this before. If I take any, and now we take natural numbers, because if I have an integer, I can always argue with x inverse. So let k be a natural number. Then the assertion is that the order of x to the kth power is n divided by the greatest common divisor of n and k. This is an abbreviation for the GCD. The greatest common divisor of n and k is this here, and if I divide n by that, I end up with the order of x to the k. And I think it's worthwhile to look at least two examples illustrating this formula before we move on. Okay, so for example, let the order of x be 42. Of course, 42 can be factored into primes like so, 2 times 3 times 7, so n, the order of x, is 42. Now, if I take k equal to 7, this is a divisor of n, so the greatest common divisor of these two, of course, is 7, and by the formula we just saw the order of x to the 7 is the order of x divided by the GCD, so 7, and we end up with 6. And indeed, x to the 7, this element here, to the 6th power is x to the 42, which is clearly the identity, because the order of x is 42, and 6 is the smallest such number. This is important for it to be the order, because if I take x to the 7 to the mth power, I end up with that. And if m is less than 6, this here cannot be 42, so this by definition of the order of x cannot be the identity. So indeed, 6 is the smallest natural number, such that this here holds. And I think you could have gotten that without the general formula. So the first interesting case is this here, k equals 18, and we ask ourselves, what is the order of x to the 18th power? Now the GCD of those numbers is 6. You simply take all the common prime factors to the maximum power, which here is 1, so 2 times 3, because they both occur in the prime factorization. And by this formula, the order of x to the 18th power is 42 divided by the GCD, which is 6, so the order of this element is 7. And this, at least for me, is not obvious without this formula. And indeed, you can check x to the 18 to the 7th power is x to the 126th power, but this here is 3 times 42, so this here is the identity, because I can write this as x to the 42th power, which is the identity, to the 3rd power, which stays the identity. And you need to check that this does not happen if m is less than 7. I omit that step here. So in this case, we get something new. We get the order of this element, which would not be obvious, I think. So, and we record this case as an important special case. If k is a divisor of n, then clearly the greatest common divisor of n and k is k itself, and we end up with this formula because of this here. So the order of x to the k in this case is n divided by k. This, of course, cannot be true in general, because the order needs to be a natural number, which it isn't if k does not divide n. And finally, if the order is infinite, then the order of the cyclic subgroup generated by x is also infinite. Okay, this is already much longer than I expected. Let's take a break here, and I would strongly suggest that you try proving as much as you can by yourself. Because if you follow this course, you're in a good position to at least get 1 or 2 or 3 proofs of this here done. Maybe with the exception of 4, this might be a bit tedious, especially if you haven't worked much with the GCD before, but Give the others a try, and next week maybe in the comments let me know if you could do all of the proofs by yourself. And in next week's video I'm going with you through the proofs in great detail. Okay, thanks for watching, and until then, bye bye.